Hello, we are Thomas and Paul and we are going to present you fractals. Fractals are some figures which repeat infinitely. We say they are infinitely fragmented. Look for an example at this short video. Even if we zoom more and more, the image doesn't seem to get bigger. In fact, it is just infinitely small. We can't give a size to this figure. To present fractal, we are going to show you about different examples of fractal. Then we will talk about the Van Cox curve. To end this video, we will ask ourselves if the Van Cox curve is a line or an area.
We will talk about special fractals. First, let me explain to you what is an autosimilar figure. An autosimilar figure is a figure which repeats infinitely with the same form. The Van Gogh curve we will study after is an autosimilar figure. There are other well-known autosimilar figures created by great mathematicians. The one I want to show you is the Sierpinski triangle and the Pythagoras tree. To make the first one, you have to take a triangle, equilateral, then split this triangle in 4. Withdraw the middle one and you will have 3 triangles. On each of these triangles, do the same operation that you did on the first one. If you do this operation an infinite amount of time, you will have the Sierpinski triangle. Then the other one I want to talk to you about is the Pythagoras tree. To do the Pythagoras tree, take a square, then build on the top of the square 2 other squares with the angle that meets each other's. Then on the top of the 2 new squares you have to draw 2 new squares on each. The important thing is that the ratio of the area of the squares stays the same always. In this figure we can see the same thing at any scale. To say it by another way, if you zoom again and again, you will always see the same thing in the Sierpinski triangle and the Pythagoras tree. That's why we call them autosimilar figures. Let's speak of the most beautiful type of fractals, the Mandelbrot set. First, let's talk about the mathematical part of this set. The Mandelbrot set is the set of complex numbers C for which the function f of z equals z squared plus c does not diverge when iterated from z equals 0. Now we can see 2 different parts of the Mandelbrot curve, and as you can see, this curve makes a very beautiful figure. To finish, I'm going to talk here about the fractals in nature. Per sure, there are many examples of fractals in flora. The most well-known are Romanesco, cactus or fern, but there are so many other examples like cabbage, the lotus, or even all sorts of different flowers. I am now going to talk to you about the Van Gogh curve. Helt van Gogh, born in 1870 and dead in 1924, is a famous Swedish mathematician. He is one of the many mathematicians who finds properties for fractals. For instance, he created a curve named by his name, the Van Gogh curve. Now I'm going to explain you how to build this curve because I think it's important to realize how much this curve is special. To make it easier, let's look to this video. First, you take a segment. Then you redraw a second third of this segment. In the hole you just made, draw 2 new segments with as length a third of the original segment, making a thing looking like an equilateral triangle. Then you have to repeat this operation on all the segments you currently have. If you repeat this operation an infinite number of times, you will have the Van Gogh curve. We say that it's an autosimilar figure.
Finally, we can ask ourselves if fractals are a line or a surface. First, we must talk about the special link between the length and the area. The length is one-dimensional, but the area is two-dimensional. So, when you multiply the figure by 2, the perimeter is also multiplied by 2, but you multiply the area by 4. Then, if you multiply the figure by 3, the perimeter is multiplied by 3, the area by 9, 3 times 3. To be more general, when you multiply the size of the figure by x, the perimeter is x, the area by x squared. Now, it seems legitimate to ask ourselves if Van Gogh's curve is a line or a surface. Imagine we multiply the size of the curve by 3. If this curve was a line on one direction, then the length of the curve should be 3. However, the length is 4, so the Van Gogh's curve is not a line. Now, imagine we still multiply the size of the curve by 3. We should find that the area of the curve is 9. Actually, it's not. So, the Van Gogh's curve isn't a surface. So, what is it? The Van Gogh's curve isn't one-dimensional or two-dimensional. To find the definition of the curve, we have to make really difficult calculus far beyond our level. The answer was given by Felix Hausdorff. The Van Gogh's curve is in 1.26 dimensional.
It's finished. We hope you've learned many things about fractals. If you liked this video, subscribe now by clicking here. See you next week for the next video.